Modern Additives, 1714. How was it possible that structures built over 2,000 years ago still stand strong today, while modern concrete bridges crack and crumble after just 50 years? The Romans constructed harbors, aqueducts, and massive domes that have endured millennia of earthquakes, storms, and saltwater erosion without a single piece of steel reinforcement. Their methods will absolutely challenge everything you think you know about construction and durability. Imagine standing before the Pantheon in Rome, its enormous concrete dome spanning 142 feet, completed in the year 128 AD. No reinforcing bars, no modern additives, no steel cables hidden within. Just concrete that has outlasted empires, survived countless earthquakes, and continues to inspire awe nearly 2,000 years later. Meanwhile, modern concrete structures begin deteriorating within decades, their steel reinforcements rusting and expanding, tearing apart the very material they were meant to strengthen. The Roman harbor at Caesarea, built by Herod the Great, still stands submerged in the Mediterranean Sea, its concrete growing stronger with each passing century as seawater chemically reacts with its components. Modern marine concrete in the same waters requires constant maintenance and replacement. The true genius wasn't in brute strength or massive scale, but in a profound understanding of chemistry and materials that we're only beginning to rediscover in the 21st century. The Romans didn't just mix concrete, they engineered a living material that could heal itself, adapt to its environment, and grow more resilient over time. They understood something fundamental about working with natural forces rather than against them, creating structures that became part of the geological landscape rather than foreign objects imposed upon it. Watch this video to the end to discover the specific volcanic materials they used, the exact mixing ratios that created self-healing properties, and the lost techniques that allowed their concrete to actually strengthen underwater. You'll learn why our modern approach might be fundamentally flawed, and how ancient wisdom could revolutionize construction for the next 1,000 years. There are secrets in Roman concrete that were lost for over a millennium, and what I'm about to reveal will change how you see every ancient structure you encounter. What do you think about the idea that ancient builders understood materials better than we do today? Does it challenge your assumptions about technological progress? Write your thoughts in the comments, and don't forget to subscribe to our channel to discover more lost knowledge from the ancient world. I'm going to reveal the best-kept secret of Roman construction, the one element that made everything else possible. This wasn't just a building material, it was a geological revolution that the Romans weaponized for empire. The foundation of Roman concrete was pozzolana, a volcanic ash found in the regions surrounding Mount Vesuvius and throughout the volcanic fields of central Italy. But calling it simply volcanic ash is like calling the Mona Lisa a painting. The Romans recognized at least 4 distinct varieties of pozzolana, each with specific properties suited to different applications. There was Pulvis pudiolanus, the prized reddish-brown ash from Pozzuoli near Naples, which possessed extraordinary hydraulic properties. Then came the gray pozzolana from the Alban Hills, the black variety from volcanic fields near Rome, and the white pumice powder used for lighter structural elements. Each type contained different ratios of silica, alumina, and lime, creating distinct chemical reactions when mixed with other components. This ash from Puteoli, a Roman engineer might explain to his apprentice while examining a handful of the rusty powder, will set even beneath the waves. The others will not. This wasn't superstition, it was empirical observation refined over generations. The volcanic glass particles in pozzolana, irregular and angular in shape, created a mechanical bond far superior to smooth sand. But the real magic happened at the chemical level, something the Romans understood through practice even without modern atomic theory. When pozzolana mixed with lime and seawater, it triggered a complex pozzolanic reaction. The amorphous silica in the volcanic ash combined with calcium hydroxide to form calcium silicate hydrate, the same compound that gives modern Portland cement its strength. But unlike modern concrete, which completes this reaction relatively quickly and then begins a slow decline, Roman concrete containing pozzolana continued reacting for centuries. The presence of aluminum in the volcanic ash created additional compounds, tobermorite, and phillipsite that filled microscopic cracks as they formed. This is the genius of the design. The concrete didn't just endure damage, it actively repaired itself through ongoing chemical processes. The hydraulic properties of pozzolana-based concrete meant the Romans could build in conditions that would be impossible with ordinary lime mortar. They could pour concrete directly into seawater for harbor construction, create massive underwater foundations, and construct aqueducts that carried water for hundreds of miles without leaking. This was the foundation of Roman power. Quite literally, their ability to build permanent harbors opened trade routes across the Mediterranean. Their aqueducts allowed cities to grow far beyond the limits of local water supplies. Their bridges and roads created an infrastructure network that enabled rapid military deployment and economic integration across 3 continents. Think about the implications. Without pozzolana, there would be no Roman Empire as we know it. The Colosseum, the Baths of Caracalla, the vast harbor complexes that fed 1 million people in Rome itself, all depended on this volcanic material. The Romans didn't conquer through military might alone. They conquered through superior infrastructure that only their concrete technology made possible. Have you ever considered that geography and geology might determine the rise and fall of civilizations more than culture or politics? Are you ready to learn the truth about what the Romans actually mixed with their precious volcanic ash? Despite images of slaves mindlessly hauling stones, the reality was a sophisticated understanding of aggregate selection and proportional mixing that rivaled modern engineering specifications. The Romans didn't just use any rock or sand for aggregate. They carefully selected materials based on the structural requirements of each project. For foundations and massive walls, they used cementa, fist-sized chunks of broken stone, usually tufa, travertine, or basalt. These weren't random rubble. Each piece was roughly shaped to nestle together efficiently, creating a dense matrix with minimal voids. For lighter vaultwork and upper stories, they employed pumice stone, which reduced weight without sacrificing too much strength. In the dome of the Pantheon, you can observe a deliberate gradation. Heavy basalt aggregate near the base transitioning to lighter volcanic stone in the middle sections, and finally pumice near the crown where weight needed to be minimized. The lime used in Roman concrete deserves equal attention. This wasn't the bagged quicklime you might purchase today. Romans produced their lime by heating limestone or marble in specialized kilns called fornaces, reaching temperatures between 900 and 1,000 degrees Celsius. The resulting quicklime, or calyx viva as they called it, was intensely reactive. Workers had to slake it carefully by adding water, a process that released tremendous heat and created clouds of steam. Stand back when you add water to fresh lime, a master builder might warn his crew, or you'll lose your eyebrows and more. The slaking process had to be controlled precisely. Too much water and you'd get a weak paste. Too little and dangerous lumps of quicklime would remain in the mix, causing problems later. The typical mixing ratio for structural concrete followed what we'd call a 1.2.3 proportion. 1 part lime to 2 parts, pozzolana to 3 parts aggregate. But this varied significantly based on application. For waterproof cisterns and aqueducts, the ratio might shift to 1.12, increasing the pozzolana content to enhance hydraulic properties. For massive foundation work where ultimate strength mattered more than water resistance, they might reduce pozzolana and increase aggregate to 1.25 or even 1.2.6. These weren't written specifications followed blindly. They were flexible guidelines adapted by experienced builders who understood their materials intimately. The mixing process itself was labor-intensive and deliberate. Workers would combine dry lime and pozzolana first, mixing them thoroughly on wooden boards or in shallow pits. Mix until you can no longer see distinct colors. The instruction might go, "The lime and ash must become one." Only then would they add water, creating a thick mortar that would be thoroughly worked before adding the stone aggregate. Unlike modern concrete, which is mixed to a fluid consistency and poured, Roman concrete was often quite dry, almost the texture of damp earth. They would layer this mixture with the stone aggregate in the formwork, tamping it down vigorously with wooden poles. This labor-intensive process wasn't a limitation, it was a feature. The reduced water content meant less shrinkage as the concrete cured, fewer cracks, and ultimately a denser, stronger material. The vigorous tamping eliminated air pockets and ensured intimate contact between aggregate and mortar. Each layer would begin setting before the next was added, creating a monolithic structure that was actually composed of numerous thin layers bonded together. For truly massive pours like the Dome of the Pantheon, the Romans employed another ingenious technique. They embedded empty amphorae, the clay wine jugs, within the concrete to reduce weight. These weren't just stuffed in randomly. They were carefully arranged in rings, their curved surfaces creating a cellular structure that distributed loads efficiently while maintaining the concrete's integrity. The result was a dome that weighs far less than solid concrete would, yet has stood for 18.5 centuries without collapsing. It was this combination of carefully selected materials, precise proportioning, and methodical construction techniques that gave Roman concrete its legendary durability. They weren't just following recipes, they were engaging in a sophisticated engineering practice that understood structural requirements, material properties, and construction methodology at a level that wouldn't be matched again until the Industrial Revolution. But what's truly remarkable is how they adapted these principles to environments that seemed utterly hostile to construction. What if I told you that Roman concrete actually grows stronger when submerged in seawater? This seems to contradict everything we know about concrete degradation, yet it's precisely what happens with their maritime structures, and understanding why reveals perhaps their greatest technical achievement. The challenge of building in seawater is formidable. Modern Portland cement concrete deteriorates rapidly in marine environments. Salt water penetrates the material, corroding steel reinforcement and causing it to expand, which cracks the concrete from within. Chemical reactions between sulfates in seawater and compounds in the cement create expansive crystals that further break down the structure. Most modern marine concrete requires replacement within 50 to 100 years. The Romans faced this same challenge 2 millennia ago and solved it without any of our modern materials or protective technologies. Their solution began with selecting the right type of pozzolana. For underwater work, they exclusively used Pulvis puteolanus, the red-brown volcanic ash from Pozzuoli that contained optimal levels of aluminum and silicon. This material, when mixed with lime and exposed to seawater, initiated a remarkable chemical process that modern scientists are still working to fully understand. The mixture didn't just set underwater, it actively incorporated elements from the seawater into its structure. The construction process for marine concrete was elaborate and fascinating. Since they couldn't pour liquid concrete underwater, the Romans developed a method using wooden cofferdam structures. They would drive oak pilings into the seabed in a double ring, creating a watertight enclosure. The space between the double walls would be filled with clay to prevent water infiltration. Then they'd bail out the water from the interior, creating a dry workspace below sea level. Within this temporary dry dock, they'd construct their permanent concrete structure using the special pozzolana mix. But they developed an even more ingenious technique for locations where cofferdams weren't practical. They created what we might call self-setting concrete bags. Workers would fill large linen or leather sacks with a dry mixture of lime and pozzolana, seal them tightly, and lower them into position underwater using ropes and primitive cranes. Make sure the bags are packed tight, a harbor engineer might instruct, and position them so water can penetrate from all sides. As seawater gradually seeped through the fabric and saturated the dry mixture inside, the pozzolanic reaction would begin. The bags would slowly set and harden underwater, fusing together into a solid mass. Once enough bags had been placed and set, they'd form a stable underwater platform that could support additional construction. The chemistry occurring within this submerged concrete was extraordinary. When seawater interacted with the lime and pozzolana mixture, it triggered the formation of aluminum tobermorite and philipsite crystals. These minerals grew within the concrete's pore spaces, filling tiny cracks and voids. Unlike modern concrete that becomes more porous and weaker over time as it's exposed to seawater, Roman marine concrete became denser and stronger. The process was slow, taking decades or even centuries, but it meant that the oldest structures were often the most durable. Modern analysis of concrete cores from the harbor at Caesarea, built around 25 BC, shows that the material is still chemically active today, nearly 2,000 years later. The tobermorite crystals continued to grow, binding the aggregate together more tightly with each passing century. This self-healing property means that even when cracks form due to earthquakes or wave action, the ongoing chemical reactions gradually fill them in. The concrete essentially repairs itself, using the very seawater that destroys modern materials as a resource for strengthening. Think about what this meant strategically. The Romans could establish permanent harbors anywhere around the Mediterranean, even on coastlines with poor natural anchorage. They could build breakwaters and quays that would last for generations without maintenance. This gave them an enormous economic and military advantage over rivals who relied on vulnerable wooden structures or were limited to naturally protected harbors. The harbor at Portus, Rome's main seaport, could accommodate hundreds of ships simultaneously, ensuring the steady flow of grain from Egypt and North Africa that fed the empire's capital. Another indispensable element in the Roman concrete system was the use of cacciopesto, crushed terracotta or brick fragments mixed with lime mortar. This material served different purposes than pozzolana-based concrete, but was equally important in specific applications. Cacciopesto came in various gradations depending on how finely the terracotta was crushed. Coarse cacciopesto might contain brick fragments the size of walnuts, creating a rough, durable waterproof layer suitable for the floors of baths or the beds of aqueducts. Medium-grade cacciopesto with particles like gravel worked well for walls that needed to resist moisture. Fine cacciopesto, ground almost to a powder, created a smooth, waterproof plaster that could be burnished to a shine. The creation process for quality cacciopesto was labor-intensive and required skill. Workers would collect broken roof tiles, discarded pottery, and bricks, preferably ones that had been well fired originally. These would be placed on stone surfaces and crushed with hammers until they achieved the desired particle size. Don't mix poorly fired brick with good, an experienced plasterer might advise. The weak pieces will absorb too much water and create soft spots in your work. The crushed terracotta would then be mixed with lime in ratios ranging from 1:3 to 1:5, depending on the application, and enough water to create a workable paste. When applied to surfaces, cacciopesto was laid in layers, each one tamped or troweled firmly to eliminate air pockets. As it cured, chemical reactions between the lime and the clay minerals in the crushed terracotta created a water-resistant matrix. The fired clay in the fragments contained reactive silica and alumina that behaved similarly to volcanic pozzolana, though with somewhat different properties. The result was a material that could waterproof cisterns, protect walls from rising damp, and create durable floor surfaces that could withstand constant moisture. The Romans discovered that by adding marble dust or crushed white stone to fine cacciopesto, they could create an attractive pinkish-white finish for high-status buildings. The heated baths of wealthy Romans often featured cacciopesto floors inlaid with elaborate mosaic patterns, the waterproof qualities of the base material protecting the structure beneath from constant water exposure. You can trust cacciopesto where even stone might fail, a bathhouse builder might say with confidence. While pozzolana came from volcanic deposits and terracotta was a manufactured product, the Romans also made extensive use of natural sand and crushed stone aggregates in situations where the special properties of volcanic materials weren't necessary. River sand, gathered from the Tiber and other watercourses, was preferred for many applications because it was naturally washed and contained fewer impurities than sand from beaches. "Beach sand carries salt that will weaken your mortar," Vitruvius wrote in his architectural treatise. "Use river sand when you can." The sand was often sorted by size using sieves made of woven horsehair or bronze mesh, separating fine sand suitable for finishing work from coarser material better suited to structural applications. When natural sand wasn't available or didn't have the right properties, the Romans would manufacture their own by crushing stone. Quarries would produce crushed stone aggregate as a byproduct of their main operations, gathering the fragments that broke away during the cutting of building blocks. Different stones produced different qualities of aggregate. Crushed basalt created hard, angular particles excellent for high-strength concrete. Crushed travertine was softer and easier to work but still produced durable results. Crushed marble, reserved for decorative work, created a bright white aggregate, that could be used in specialized plasters and fine finishes. The Romans understood that the quality of aggregate mattered as much as any other component. They knew that aggregate contaminated with clay would produce weak concrete. They recognized that smooth, rounded particles didn't bond as well as angular, freshly crushed material. They observed that certain stones absorbed too much water and would cause problems in the final product. This knowledge was empirical, built through generations of trial and error, but it was nonetheless precise. The final element that made Roman concrete remarkable was fresh water, and not just any water would do. The Romans were particular about using clean, pure water for mixing their concrete, understanding that contaminated or salty water could compromise the final product. For most construction, water was drawn from aqueducts or clean wells. The same infrastructure that supplied drinking water to cities also served construction sites. Use water you would drink to mix your mortar was the simple rule. This ensured that the water was free from harmful minerals, organic matter, or excessive salts that might interfere with the chemical reactions that gave concrete its strength. In hot weather, workers might cool the mixing water by storing it in clay vessels placed in shade or even adding ice when available. The temperature of the water affected how quickly the lime reacted and how much time workers had to place and work the concrete before it began to set. Cooler water meant slower reactions and more working time, crucial for large projects where coordination among numerous work crews was essential. During winter, the opposite problem arose. Freezing temperatures could prevent the concrete from setting properly, and water within freshly placed concrete could freeze and expand, creating cracks and weakness. The Romans dealt with this by adding hot water to their mixes during cold weather, and sometimes by covering fresh concrete with straw or cloth to insulate it during the critical early curing period. They also added substances we might consider primitive admixtures, animal blood, milk, or egg whites, which altered the setting characteristics and improved workability. A little milk makes the mortar flow more smoothly, a plasterer might note, sharing knowledge passed down through his craft. The combination of all these carefully selected and prepared materials, mixed in appropriate proportions and worked by skilled hands, created concrete that wasn't just a building material, but almost a living substance that continued to develop and strengthen over centuries. Yet even with all their knowledge, all their careful preparation, and all their superior materials, the Romans faced situations where their concrete technology couldn't solve every problem. There were limits, failures, and moments when even the best engineering had to yield to overwhelming forces. Imagine the aftermath of a major earthquake striking a Roman city. Walls cracked, structures compromised, and builders faced with the urgent need for repairs. Or consider a military campaign where Roman engineers had to construct fortifications far from volcanic ash sources, unable to access the materials that made their concrete legendary. These moments tested the limits of their technology and forced innovations in repair, adaptation, and emergency measures. When major cracks appeared in important structures, Roman engineers developed sophisticated repair techniques. They would widen the crack deliberately, creating a V-shaped groove, clean it thoroughly of loose material, and then pack it with fresh mortar containing a high proportion of pozzolana or cacio-pesto. Sometimes they'd drill holes on either side of a crack and insert bronze or iron clamps, anchoring them with lead to tie the fractured sections back together. A visible repair, honestly done, is better than a hidden weakness, a restoration specialist might explain to patrons worried about the appearance of their repaired building. For structures built far from sources of volcanic ash, the Romans had to make compromises. In Britain, Germania, and other provinces where pozzolana wasn't available, they reverted to simpler lime mortars that didn't possess the same hydraulic properties or longevity. These structures have generally fared worse over the millennia, proving that Roman concrete's reputation for durability really did depend on those special volcanic materials. Some innovative provincial engineers experimented with grinding local clay tiles into powder as a substitute for pozzolana, creating a primitive version of cacio-pesto that offered some improvement over plain lime mortar, but it never matched the performance of true pozzolana-based concrete. The most desperate situations arose when structures failed catastrophically. When a vault or dome collapsed during construction, a failure that did occasionally occur despite Roman engineering prowess, The economic and human cost could be devastating. Tons of concrete and stone would crash down, potentially killing workers beneath and destroying months or years of labor. We pulled 17 men from the rubble, an ancient record might note with stark brevity, and could save only 4. The rebuilding process after such disasters required careful investigation of what went wrong. Did the formwork fail prematurely? Was the concrete mix wrong? Did the design push too far beyond proven limits? These failures, though traumatic, taught crucial lessons that were incorporated into evolving practices. The Romans learned from mistakes, adjusted their methods, and pushed forward with increasing confidence. The fact that so many Roman concrete structures still stand is partly because they learned what not to do through painful experience, refining their techniques over generations. Roman concrete technology wasn't simply about mixing volcanic ash with lime and aggregate. It was a comprehensive system of knowledge encompassing geology, material science, structural engineering, and construction methodology. The genius lay in their empirical understanding of how different materials behaved and interacted, knowledge they accumulated through careful observation across generations. They understood that pulvis puteolanus from Pozzuoli could set underwater. They knew that cacio made surfaces waterproof. They recognized that certain aggregates created stronger concrete than others, and that the proportions needed to shift based on the application. They developed construction techniques like using dry mix concrete tamped in layers rather than fluid concrete poured all at once. They invented cofferdam technology and underwater construction bags. Each innovation built upon previous knowledge, creating an increasingly sophisticated practice. The unifying philosophy behind all Roman concrete work was remarkably modern in one respect. They worked with materials according to their natural properties rather than trying to force materials to behave against their nature. They accepted that lime mortar by itself wasn't waterproof, so they added pozzolana or cacio to give it that property. They understood that concrete had tremendous compressive strength, but poor tensile strength, so they designed arches, vaults, and domes that kept the material in compression. They knew that different environments demanded different approaches, so they varied their mixtures and techniques accordingly. This flexible, empirical, property-based approach to materials was genuinely sophisticated. The legacy of Roman concrete is complex. After the fall of the Western Roman Empire, much of this knowledge was lost. The sources of pozzolana remained, but the systematic understanding of how to use it effectively vanished. Medieval builders could create lime mortar, but they couldn't replicate the hydraulic cements or the massive unreinforced concrete structures of Rome. It wasn't until the 18th and 19th centuries that engineers began rediscovering pozzolanic materials and developing Portland cement as a modern equivalent. Even today, as we study why Roman concrete continues to strengthen in seawater while modern concrete degrades, we're essentially rediscovering knowledge that was common practice 2,000 years ago. What other aspects of Roman engineering and construction would you want to explore? Perhaps their road-building techniques that created highways lasting 2 millennia, their aqueduct systems that moved millions of gallons daily using only gravity, or their sophisticated underfloor heating systems that made marble bathhouses comfortable even in winter. Suggest topics for future videos in the comments. And if you want to continue discovering the lost knowledge and engineering genius of ancient civilizations, subscribe to our channel so you don't miss our next journey into the remarkable achievements of the past. There's so much more to uncover about how ancient builders accomplished what we struggle to replicate even with modern technology.